I'll be walking through combined spectral problem F. So I had C7H14O2. So immediately I calculated the hydrogen deficiency index. So there's supposed to be 16, there's 14 hydrogens, so we can see we're missing one pair of hydrogens, which keys me into a double bond somewhere. So when we go down and look at the IR spectroscopy, see the common peak for sp3 CH stretch. I don't see any broad OH tongue or an aldehydic sp2 stretch. Go over here, we see the common carbonyl stretch at about 1720, I guesstimated, it looks like. And then you continue on, see between 1000 and 1200 a couple of tetrahedral CO stretches. Right, so kind of looks like we might have an ester, but we'll keep going and see what the carbon-13 NMR shows. So right here, immediately, between the 160 and 190 site for carbonyl, we have a signal here between 160 and 190 carbonyl for ester, amide, or acid. Like we said earlier, we don't see any OH stretches, so doesn't look like we have an acid. There's no nitrogen in our formula. So I'm pretty keyed in for an ester here. And then you continue on past the 100 part per million mark. We start looking at our sp3 tetrahedral portion. See at 60 the peak for tetrahedral CO bond. And then if you move over, we see just past the 40 a carbon-to-carbon bond, but it's, as you can see, it's more downfield than the non-dipole sp3 carbon-to-carbons. So you can kind of tell it's closer to this ester. It's less shielded and closer to that electronegative atom. We can also tell from the 13 carbon NMR, there's 6 peaks here, right, showing 6 unique carbons. We know that we're supposed to have 7 carbons, so that tells us that 2 of them are symmetrical. So we'll keep that in mind as we go down to our proton NMR. So for the proton NMR, we have 5 signals, so 5 unique set of protons. Annotated the chemical shifts here. These labels aren't in any specific order. I just worked from upfield, downfield, and labeled as such. I did measure these peaks in millimeters, just kind of rounded up to the most round number that would be easiest divisible by. And it seemed to work out. We got good numbers that add up to the hydrogens that we're meant to have per the formula. So divided the smallest by itself and by the rest of them, so 4 divided by 4, 1 hydrogen, 8 divided by 4, 2 hydrogens for these, 12 divided by 4, 3 hydrogens, and then 24 divided by 4, and we have 6 hydrogens here. And you can see it kind of matches up based on the height that we see in the spectrum, right? This is about double the 3 hydrogen. The neighbors were very easy to identify just because this spectrum is very clear. It was easy to count the peaks. So for HA, 2 peaks, so 1 neighbor, right? We minus itself so we can get the amount of neighbors. 2 neighbors for these 3 peaks, 6 neighbors, we have 7 peaks here, 1 neighbor for 2 peaks, and then 3 neighbors for these 4 peaks here. So splitting was pretty easy to identify. We go down. Our tables basically show everything I just went over. We have the classic sp3ch stretches and the IR frequency. Saw the classic carbonyl stretch, and then two stretches indicative of the tetrahedral CO stretches. And then in our 13 carbon, like I said, we saw that peak indicative of a carbonyl that's part of an ester. And then we saw the CO sp3 peak to support that ester. And then we saw a carbon to carbon bond that's very close to that electronegative atom. It's furthest from the more upfield sp3 non-dipole carbon to carbon bonds. So in this table, put everything that I just showed you on the spectrum and how I interpreted that. So this one, most downfield, two hydrogens, and it's a quartet. So I'll go through the interpretation as I kind of show you how I got the structure, right? So first thing I did was draw the ester. I knew for a fact that we had an ester, so I drew that out. And then this is clearly most electronegative or closest to that electronegative atom. It's at 4.0 within that range. So figured it was a CH2 based on the two hydrogens. It's a quartet, so it must have three neighbors. So I immediately made that CH2 bonded to the oxygen because it's so de-shielded and downfield, right? So there's the CH2. Just as a placeholder, I wasn't sure yet, but I put in the CH3 so it could have its three neighbors and I could work from there. And then the next most closest to that electronegative carbonyl would be at 2.4, not directly bonded clearly because it's way below the 4.0 parts per million, but closer than the rest of our alkanes. So 2H, so CH2, it's a doublet, so it has one neighbor. And again, I'm assuming it's near the carbonyl. So I went down here, put in our CH2. I'm assuming that that one neighbor is a CH. So again, as a placeholder, I kind of put that CH in there and went back up to see what else we had left. And then at 2.2, 1H, so there's the CH that I had assumed was there. And it's a septet, so it has six neighbors. I went ahead and thought two CH3s, possibly two methyls. So it works with the CH. It has two more bonds to make. So I put a methyl on either side and then went up to confirm kind of because I kind of already had it built out. So when I went back up to the table at the 1.2 chemical shift, three hydrogens. So there's that methyl on the end here, and it's a triplet, so it has two neighbors. That works. There's our CH2 there. And it even works too with the chemical shift because it's still more downfield than this one, which makes sense. It's, you know, 1, 2, 3 bonds away from an oxygen, whereas these two CH3s here, 1, 2, 3, 4, about 5 bonds away from an oxygen. So even the chemical shift works as well. So those 6 hydrogens, I'm assuming, are those 2 methyls. It's a doublet, so it has one neighbor. So there's our 2 methyl groups, and it's one neighbor on the end there. And then here's the structure, and I labeled it based off of the labels we have up here. You can see H, A, B, C, D, E. Like I said, the labels weren't made prior, obviously, because we didn't have the structure, so they're kind of out of order, but they're based off of um, this spectrum. All right, thank you for watching my video.